Okay. Can everybody see my slide with gallium on it now? Okay, so what I'm trying to get at is that you have to know how to use your calculator. And I'm sure there's somebody out there that's thinking, come on, I know how to use my calculator. Oh, you'd be shocked. If you're a chemistry teacher, you would be shocked. I've had a student, not you guys, of course, but it was a spring 2019. I was giving the first exam, face to face, a paper exam, and somebody put up their hand and they said, how do I use scientific notation? Well, that tells me the person never did a single practice problem with their calculator, So make sure you know how to use your calculator moving forward in this class. All right, and if you don't know how to, if you Google it on YouTube, there's all kinds of videos that show you how to use your calculators. Okay, whether it's a Texas Instruments or a Sharp or whatever. It says here, let's try another problem. Iron, Fe, is the main component of steel and therefore the most important metal in society. I thought it was heavy metal. Anyhow, it is also essential in the body. How many iron atoms are there in 95.8 grams? So you can see here that now we're going to have to break out two conversion factors, right? Because we have to take that grams and we can't convert that directly to number of atoms, right? There's no way to do that. The first thing we're going to have to do is convert that to the number of moles, and then we know how many atoms of iron there are in a mole, right? There's Avogadro's number. So let's give that the old college try here. So we're going to start it with 95.8 grams of iron, and we're going to multiply that by this conversion factor, the molar mass of iron. So 1 mole of iron has 55.85 grams of iron, and of course I got that from the periodic table. Again, you can see that the units are canceling out. But if we were to stop right here, if I put an equal sign, I would end up with moles of iron. I want the number of atoms of iron. And I know that in 1 mole of iron, there's going to be Avogadro's number of atoms of iron. So 6.022 times 10 to the 23 atoms of iron. And looky, my units cancel out, moles of iron, and I'm left over with atoms of iron. So when I punch all that spinach into my calculator, I end up with 1.03 times 10 to the 24 atoms of iron. You can kind of check this in a way, right? Because think about it, 1 mole of iron weighs 55.85 grams, and you're starting with 95.8. So you have more than a mole. So the number, your final answer, should be bigger than Avogadro's number. So that makes sense. All right, so just some kind of thought processes that you might want to have when you're solving problems like this. Give me a thumbs up if you think you can do that one. Cha, anybody? Think they could do that one? Let me scroll down here. Yeah, all right. Okie doke, good. Great, as they say in Scottish. Well, let's keep moving. Here's the solution. What else? Want to try another one? Does anybody like doing practice problems in class? Just me?
Yes.
Okay, good, because I do too. I enjoy. Somebody says yes. Okay, that's great. So, hey, I do too. I really enjoy doing practice problems with my students. It's not as fun on Teams as it is face-to-face because I like running around the classroom and just seeing like who's got what for an answer. It's always fun. But let's give this one a try as a group. It says here, nitrogen dioxide. Hey, little nomenclature practice, right? NO2, molecular compound made of 2 nonmetals. It's a component of urban smog that forms the gases in car exhausts. How many molecules are in 8.92 grams of NO2, nitrogen dioxide? Look, this is almost identical to the last problem, okay? But now we just had to calculate the molar mass of NO2. And it says here that the molar mass of NO2 is 46.01 grams per mole. Where did you get that? Well, the mass of nitrogen is 14.01, and the mass of oxygen is 16. So NO2, right, the molar mass of NO2 is going to be equal to 14.01 plus 2 times 16.00 Okay, I'll wrap this whole thing up in grams per mole because I'm too lazy to write the units a bunch of times. And you end up with 46.01 grams per mole. There we go. Let's try it. Let's give it the old college try. Let me just scroll up here a little bit. And I'll break out the red pen. We're going to start with 8.92 grams of NO2. Here's our conversion factor laid out for us right here. We know that when we have 46.01 grams of NO2, we've got 1 mole of NO2. And looky, our units cancel out beautifully. If we were to stop right here, we would have the number of moles of NO2, but we need to figure out the number of molecules of NO2, right? NO2, nitrogen dioxide, that's a molecule. And so when we multiply all this out, we put that in 1 mole of nitrogen dioxide, we end up with 6.022 times 10 to the 23rd molecules. I'll put molecules of NO2. Whoop, there we go. We're going to put all that spinach into our calculator, and we're going to get the correct answer. I did this one. In fact, I think I did all of these. I end up with 1.17 times 10 to the 23 molecules of NO2. Beauty, just like that. All right. Well, with that in mind, let's keep moving. All right, and you can see how dimensional analysis is a very powerful tool in chemistry. Another thing that I'll point out here is I'm going to come off sounding like a dad a little bit, but I am a dad, so I have the right to act like one. And look, if I can encourage you, and I like to encourage my students, I don't ever want to discourage anybody. If I can encourage you while you're studying in chemistry, always include your units. Please, for the love of Pete, can you just put them in? I know it takes an extra few seconds to write things like the letter M, then the letter O, then the letter L, then like NO2, right? See, like my arm is sore already, but I'm telling you, it's worth it, okay? I can't tell you how many times, and I might have even told you this, I forget what I say to every class, but I had a student in that same class where the person hadn't used a calculator, and I said, for the love of Pete. Anyhow, so I had a student in that class who I only carry enough ink in my pen to write answers. Well, you better get a bigger pen, Jonah, or a bigger pencil, all right? So look, I had a student in that class who was an excellent student. He's now in, chiropractor school, I think. Anyhow, so that guy's in chiropractor school. And I remember he got a grade on an exam. He was really unhappy about it. Just like, oh, Mr. Deon, this, come on, what happened here? I said, I don't know. Let's look through your scratch paper. So we looked through it, and I was like, Chris, there is not a single unit anywhere here. I have no idea what's going on, in a lot of these answers. And so that was what he left out. He just neglected to put in units in, in 2 or 3 problems, and his grade went from an A to a B, and he was really unhappy about that. So always keep your units in. All right, with that in mind, what's this one here? It says ammonium carbonate. Good. Ammonium carbonate is a white solid that decomposes on warming. It's also a component of baking powder. How many formula units are in 41.6 grams of ammonium carbonate, and how many oxygen atoms are in this sample? Okay, so when it says here formula units, don't get thrown off and be like, what the heck is a formula unit? Okay, formula units, the only reason it says that instead of molecules is because ammonium carbonate is ionic, right? Ammonium carbonate is an ionic compound. Ammonium is a cation, right? Ammonium, NH4, and carbonate is CO3 2 minus. So when I put them together, I end up with NH4 2 CO3. And so you can see how in a question we can ask you nomenclature while asking you, stoichiometry, which is what we're working on today. So now we have the formula of ammonium carbonate shown here, and we want to know how many formula units there are in 41.6 grams of ammonium carbonate. Well, the first thing we have to do is figure out what the stinking molar mass is for ammonium carbonate. Now, I've gone ahead and done that on the next slide. So I went ahead and I worked out the solution to the formula mass. Notice I'm not saying molecular mass, I'm saying formula mass. of ammonium carbonate, which is 96.09 grams per mole. So now if we want to figure out the number of formula units, let's go back to our question here. It says we're starting with 41.6 grams of ammonium carbonate. All right, so let's write down what we have. We've got 41.6, jeepers, I got a short memory, of 41.6 grams of ammonium carbonate, okay? Then we're going to multiply that by this conversion factor. I know that in 1 mole of ammonium carbonate, this is getting tiring, Jonah, has 96.09 grams of ammonium carbonate, okay? So my grams, did I leave out grams there? Good grief. Okay, grams are there. So we're going to eliminate grams of ammonium carbonate. And I've got moles of ammonium carbonate, and I know that in 1 mole of ammonium carbonate, okay, since this is ionic, I'm going to have Avogadro's number of formula units. So we're going to put 6.022 times 10 to the 23rd. I'll put here form units of ammonium carbonate. After that big lecture I just gave you about writing your units, I'm getting tired. Anyhow, we got moles of ammonium carbonate canceling out. And when you punch all that spinach into your calculator, you end up with 2.61 times 10 to the 23rd formula units of ammonium carbonate. Couldn't we have just picked carbon monoxide, made it simpler? Anyhow, there you go. So that's the number of formula units. All right, let's move on from there. There's the solution. Oh, for the number of atoms, well, you can figure out how many atoms there are per formula unit, right? You can see that in 1 formula unit of NH4 2CO3, there's 3 oxygen atoms. So you would multiply the number of formula units, right, by this conversion factor. So you have 3 oxygens for every formula unit, and you end up with the number of oxygen atoms. All righty. Who's enjoying this? Is it just me? I find this pretty exciting. All right, Violet is. Okay, thanks, Violet. 1 person, I'll take it. Okay, ecstatic. Wow, this is good. Chemistry's moving up in the world. All right, let's see here. Mass percent from a chemical formula. I bet you if I ask you, I fell off the edge of my seat an hour ago. Yeah, good. Okay, you got to make sure you lay off the, anyhow. All right, so mass percent from the chemical formula. Mass percent, I don't like to use the word simple in chemistry in the same sentence because chemistry is not simple. But I'd say this is one of the simpler formulas that we look at. If you want to figure out the mass percent of any element in a formula, you just take the mass of that element and you divide it by the total mass of the compound, multiply by 100%. Okay. Let's take a look at an example, right? The best way to do it is to take a look at an example. You know what? I think there's an even faster way to write this out, okay? Let me give you Mr. Deon's abridged version, okay? The mass percentage of an element, you could also just say it's mass of, element X, so we'll say mass of X in grams, divided by the mass of the compound. Okay, I just noticed that I had that written in my notes here, multiplied by 100%, okay? That's simpler, right? Because here they're saying you're multiplying moles by grams per mole, so that cancels out, and you end up with grams over grams. Those cancel out, and then you multiply by 100%. Either way is fine, totally fine. And if you're like, what the hell is this? Let's just take a look at an example. It says here, the effectiveness of fertilizers depends upon their nitrogen content. Ammonium nitrate, so you should be able to come up with the formula for ammonium nitrate. Ammonium, as we spoke about earlier, ammonium is NH4 plus, nitrate is NO3 minus. You put those together and you end up with NH4NO3. So there's ammonium nitrate, common fertilizer. What's the mass percentage of each element in ammonium nitrate? Good gravy, okay? Well, let's do a couple of them anyhow. The first thing we should do, jeepers, I didn't help myself out very much here. The first thing we should do is we should figure out the formula mass of ammonium nitrate. And so I'm not going to show you all the math. I've gone ahead and done that already here in my notes. But ammonium nitrate, I look up on my periodic table the mass of 2 nitrogens, the mass of 4 hydrogens, and the mass of 3 oxygens. When you tally all that up, you get the formula mass of ammonium nitrate, which is 80.05 grams per mole. Okay, so I've got that. That's where I'm starting. And it's saying figure out the mass percentage of each element. Well, I'm talking about, like, think about this. If you had 6.022 times 10 to the 23 formula units of NH4NO3, how much is it going to weigh? It's going to weigh 80 grams, okay? 80 grams is about what? Maybe a little less than a quarter of a pound, okay? So everybody in the room could pick that up and throw it, okay? And, right, 80 grams doesn't weigh a lot. But in that 80.05 grams, how much of that mass is nitrogen, how much of that is hydrogen, and how much of that is oxygen? Well, all we do is we look up the mass for any element on the periodic table. And I know that the mass percentage of nitrogen is going to be equal to, who can tell me how many nitrogens are in this compound? How many nitrogens are there in NH4NO3? Thanks, Matthew. Exactly. There's 2, right? It wasn't a trick question. So we're going to take 2 times 14.01 grams per mole. Okay. And then I'm going to divide that by the whole molar mass. Now, if you're like, well, hey, Mr. Deon, in the formula that you had before, you didn't have moles in there. Okay. I can just assume that it's a mole. So if you're like, if it makes you happier, if you're like, you want me to delete moles, look at me. I'm using my Apple Pencil and just deleting it, okay? Because we're just talking about a mole. Shit, I can use it, right? Anyway, we're talking about a mole, okay? And then I'm going to multiply that whole spinach by 100%. So if I take 28.02 divided by 80.05, and I multiply that by 100%, I end up with 35.00% nitrogen. Give me a thumbs up if you follow me on that. This is not meant to be anything mind-boggling, really. And we do look at some things in this class that are kind of mind-boggling. Cha, anybody? No? Okay, maybe. Okay, I get some thumbs up. Sorry. Can't see my chat. Yeah, that makes a lot of sense now. Good. Thanks, Emma. Let's take a look. What about hydrogen, Emma? What would the mass percentage of hydrogen be? Well, how many hydrogen atoms are there? There's 4 of them, okay? So if I want to do it for hydrogen, I'm going to take 4 times the molar mass of hydrogen, which is 1.01 grams, right? And I'm going to divide all of that by 80.05 grams. So if I take 4.04 divided by 80.05, I need more lights in here. Multiply that by 100, I end up with 5.05% of hydrogen, okay? If I want to figure out the percent of oxygen, all I have to do is take 100%, right? Mass percent of O. I just take 100% and I subtract 35.00% and I subtract 5.05%, okay? And that's going to give me the answer for the mass percentage of oxygen. Did I work it out? I don't know. I do lots of things. It's 59.96, okay? 59.96% oxygen, okay? That's all it is, figuring out mass percent in a compound, not meant to be anything, to shake your foundation. All right, and here's the solution, all worked out for you beautifully. Look at that. All right, and the check and everything. Let's talk about mass fraction. Mass fraction is pretty analogous to mass percent, except instead of using mass, we use moles. Okay, so mass fraction and the mass of an element. So mass fraction can also be used to calculate the mass of a particular element in any compound. Sorry, I'm getting ahead of myself here, aren't I? Mass fraction. So if I want to figure out the mass of an element in a sample, okay, so let's say we have a sample of a compound, but we don't have a mole of it, right? We have less than a mole or more than a mole. Well, if you want to figure out the mass of an element in that sample, what you do is you take the mass of the compound, okay, and then you multiply it by this conversion factor, the mass of the element in 1 mole of a compound, which is what we just did, divided by the mass of the 1 mole of the entire compound. And if you're like, show me an example, Mr. Deon, let's do it. It says here, use the information from the last problem that we did to determine the mass of nitrogen in 650 grams of ammonium nitrate. Well, look, let's back up. I'm not going to scroll all the way back there, or do I have to? No. Okay. I calculated the molar mass, or the formula mass of ammonium nitrate was 80.05, and that the mass percentage of nitrogen, will this work if I copy it here? Copy. Can I paste it in another slide? Let's live dangerous here. Dangerously. Boom! All right. So we figured out in the last problem that the mass percentage of nitrogen in ammonium nitrate, remember ammonium nitrate was NH4NO3, and it says, what's the mass of nitrogen going to be if I have 650 grams of ammonium nitrate? Well, I mean, what's the fraction out of 1? If I have 35%, it's 0.35, right? So all I have to do is take if I want to determine the mass of nitrogen, I take my 650 grams, I'm going to put the decimal in there, so there's 3 sig figs of ammonium nitrate, multiplied by 0.3500 grams of nitrogen in 1 gram of ammonium nitrate. Oops, ammonium nitrate. Like that. You can see that grams of ammonium nitrate cancel out, and I'm left over with 228 grams of nitrogen. Okay, so if you're wondering, like, where did you get that conversion factor, Mr. Deon? Well, remember, if you have 100 grams, it's got 35 grams of nitrogen. So I just converted it to 1 gram. If you wanted to put 30, if this conversion factor, if you use 35 grams divided by 100, you're going to end up with the exact same answer. Okay, so either way works. All right, there we go. And there's the solution worked out for you. So let's talk about empirical formulas and molecular formulas for a second. Get some new definitions down here. An empirical formula is the simplest formula for a compound that agrees with elemental analysis. Elemental analysis is a technique. It's, it's basically where they take a compound, and I am not an expert in elemental analysis. I've had it done for me many times, but I've never run one myself because it's usually a person who's an expert in it that has to run the instrument. But basically, it analyzes a compound, and it tells you the percentage of each element in that compound. Sometimes it could be used to maybe identify metabolites or something. Anyhow, but an empirical formula is the simplest formula for a compound that agrees with the elemental analysis. It shows the lowest whole number of moles and gives the relative numbers of atoms of each element present. So it says here, the empirical formula for hydrogen peroxide is HO. So the molecular formula for hydrogen peroxide is actually H2O2. So all an empirical formula is what's the lowest whole number ratio that you can have? Well, if you divide the whole thing by 2, right, you'd get HO. So that's what an empirical formula is. I'll give you another example. If you have glucose, which is C6H12O6, the empirical formula, again, is the lowest whole number ratio of these elements. So if you were to divide this whole thing by 6, you'd end up with CH2O. Okay, so that would be an empirical formula for glucose. All right, so empirical formulas. It says here, determining an empirical formula from the amounts of elements. It says here, a sample of an unknown compound contains 0.21 moles of zinc, 0.41 moles of phosphorus, and 0.56 moles of oxygen. What is its empirical formula? Well, what we're going to do is we're going to find the relative number of moles of each element. So that's been provided for us, okay? And then we're going to divide by the lowest mole amount to find the relative mole ratio. So we're going to compare these three numbers of moles right here. So we have 0.21 moles of zinc, we have 0.14 moles of phosphorus, and then we have 0.56 moles of oxygen. Okay, so it says to divide by the lowest mole amount. What's the lowest mole amount out of all three of those? It's 0.14, right? That's the lowest number out of all three of those. And so let's give it a try. And I think I have it worked out for us here. So this is one where I'm not going to walk through the whole thing with you. But if you take each one of those, okay, and you divide it by 0.14, right, which is the lowest number, we end up with these numbers. So we end up with these interesting numbers, 1.5, 1, and 4.0. Now remember, what we've been given is that we were told we have 0.21 moles of zinc, 0.14 moles of phosphorus, and 0.56 moles of oxygen. Okay? There's no such thing as Zn, zinc 0.21, phosphorus 0.14, right? We can't have fractions in our formula. Okay, and we spoke about that in chapter 1. Okay, but we're trying to figure out what would the simplest whole number ratio of these be. Okay, so again, if I divide each one of these by 0.14, I get these three numbers that I have highlighted in yellow. Okay, 1.5, 1, and 4.0. Now, there's no such thing as this. There's no such thing as zinc 1.5, phosphorus 1, and oxygen 4. But what if I multiplied the whole thing by 2? Okay, if I multiplied everything by 2, then I get completely whole numbers. I'd end up with 3 zincs, 2 phosphorus, and 8 oxygen. And that would give me an empirical formula. Okay, because the empirical formula has to have whole numbers. All right, well, with that in mind, let's look at this example here. It says, analysis of a sample of an ionic compound yields 2.82 grams of sodium, 4.35 grams of chlorine, and 7.83 grams of oxygen. So literally, the person has a sample of some kind of compound and what's in that compound, okay? They know that it's made up of sodium, chlorine, and oxygen, okay? But they don't know what the empirical formula is, and they're just trying to figure that out, and from that, they're going to get a name for that compound, okay? All right, well, how are we going to do that? It says to find the relative number of moles of each element. Where are we going to go to determine the relative number of moles? Because we're given grams. Who could tell me what I would want to do here? I'm given grams, and I want to get the number of moles. Where would I have to go to figure out the number of moles of sodium and chlorine and oxygen?
Use the periodic table to convert it.
Darn right. Exactly. I'm going to go look up the molar masses of every single one of these elements. Okay. Now that's a lot of scribbling during lecture time. And so I've gone ahead and I've started the problem for us. And so right here, I've taken each one of these elements and I've multiplied them by the same conversion factor, the molar mass of the element. So grams of sodium cancel out, and I end up with 0.123 moles of sodium. Grams of chlorine cancel out. Again, I got this from the periodic table, and I end up with 0.123 moles of chlorine. Hey, right away, you can see that the ratio of sodium to chlorine is going to have to be 1 to 1. It might be 2 to 2, it might be 3 to 3, but it's always going to boil down to 1 to 1. Do the same thing with oxygen. Grams of oxygen, and that cancels. We end up with 0.489 moles of oxygen. Now, I'm being kind of silly here, but there's no such thing as Na 0.123, Cl 0.123, and oxygen 0.489. That doesn't exist, right? We have to determine what would be the lowest whole number ratio based off of these, decimal numbers here. Okay, so what we're going to do is we're going to divide each one of these by 0.123. Okay, so if I take each one of these and I divide it by, I put the wrong number here. If I take each one of these and I divide it by 0.123, 0.123, 0.123. Well, in that case, I'm going to end up with, and I'll write it down here in black ink, I end up with 1 sodium, right? 1 chlorine. And if you take your calculator and you take 0.489 and you divide it by 0.123, you end up with 3.97, which is pretty dang close to 4. And so I end up with oxygen 4, okay? They might not work out to be exactly, but literally you get 3.9756, you know, spinach, okay? So that's close enough. Now we leave out the subscript 1 in a formula. And so the formula of this compound is going to be Na, or the empirical formula is NaClO4. Could anybody name this compound for me? Somebody peruse my nomenclature videos in detail. You can tell me the name of this compound, NaClO4.
Hypochlorite. Maybe?
So hypochlorite is this. Is when you have ClO minus like this. That's hypochlorite. Okay. Chlorite. If you have ClO2 minus, that's chlorite. If you have ClO3 minus, that's chlorate. And if you have ClO4 minus, which is what we have here, you have perchlorate. Okay? So perchlorate. And so we have sodium and perchlorate. So the name of this compound is sodium perchlorate. Like that. Sodium perchlorate. Okay. There we go. Determining molecular formula. Well, we just talked about empirical formulas, okay? And so here it says the molecular formula gives the actual numbers of the moles of each element present in 1 mole of a compound. The molecular formula is a whole number multiple of the empirical formula. Sometimes empirical formulas and molecular formulas are the same, okay? But not always, okay? And so if we wanted to figure out how to determine a molecular formula, we would take the molar mass, right? The mass of 1 mole divided by the empirical mass, and whatever whole number multiple, we would multiply that by the empirical formula to get the molecular formula. If you're like, what? Well, best way to figure out anything in chemistry. Let's take a look at an example. It says here, during excessive physical activity, lactic acid, and it gives us the molar mass of lactic acid. The molar mass is 90.08 grams per mole, forms in muscle tissue and is responsible for muscle soreness. Elemental analysis shows that this compound, lactic acid, has 40% mass carbon, 6.71 mass percent hydrogen, and 53.3 mass percent oxygen. What's the empirical formula of lactic acid? Okay, so how are we going to figure this out? Well, we know the molar mass of carbon and hydrogen and oxygen, right? We can get that from the periodic table. So why don't we assume that we have a 100-gram sample, right? That's probably the easiest thing to do, is that we will assume a 100-gram sample. Because in a 100-gram sample, okay, I would have 40 grams of carbon, 6.71 grams of hydrogen, and 53.3 grams of oxygen. Well, come on, we've already done this problem based off of mass. We can determine an empirical formula. Okay, and I've already started this for us over here. If I take the mass of carbon, again, this is assuming a 100-gram sample. Okay, all I have to do is take those masses of carbon, oxygen, and hydrogen, divide them by the atomic masses in grams per mole, and I end up with the number of moles of each one of those elements. So I get 3.33 moles of carbon, 3.33 moles of oxygen, and 6.66 moles of hydrogen. So what would I do? I would divide each one of these by the lowest number. So 3.33 moles, right? 3.33 moles. You can see where I'm going with this, and 3.33 moles, okay? And then I'm going to end up with a ratio of 1 to 1 to 2. And so my empirical formula would be C1H2, right? 2, and then O1, which is CH2O. So that's my empirical formula, okay? But if I calculate the mass of that empirical formula, it doesn't equal 90.08, okay? It equals 30.03, right? I've added up the mass of one carbon, which is 12 approximately, two hydrogens, that's 14 total, plus 16 gives you 30, right? So if I take my molar mass and I divide it by the mass of my empirical formula, which is 30.03, I get 3. So then what do I have to do? I have to take my CH2O, I have to take my CH2O, and I multiply that whole thing by 3. And I end up with C3H6O3. And that is the molecular formula of lactic acid. All right, there we go. Give me a thumbs up if you follow me on that one. Figuring out, we've learned how to determine an empirical formula, and now we're just looking at molecular formula. All right, good. Well, in the interest of time, I'm going to skip the next slide, which talks about a combustion apparatus. I'll leave that as an FYI. If I have time at the end of the class, I'll talk about this. But basically, it's just a way to burn a sample and then analyze the amount of water and carbon dioxide and other gases that are produced. So that's what a combustion apparatus looks like. I've never used one in my life, but anyhow, combustion analysis was used to set up this problem right here. It's 10:21. We've got 3 hours left, so we should be able to finish lots of stuff. Okay, so it says here, if you have a 1 gram sample of vitamin C, and it gives you the molar mass of vitamin C, you put it in a combustion chamber and you burn it. You get the following data. Okay, it says you get a mass of carbon dioxide after combustion, the mass of carbon dioxide before combustion, is there something wrong with this number? Hold on, I'm just thinking out loud here. Oh no, Mr. Deon just can't read. Okay. So basically, you burn the sample, okay, of vitamin C, and then in your absorber, okay, before you started, it weighed 83.85, and then when you're done, you have 85.35. So the difference in mass here, so if you take 85.35 and you subtract 83.85, I was reading this wrong. That's why I was like, what is going on? That means that you produced 1.50 grams of CO2, and then for water, the water absorber, keepers, okay? Before you started with 37.55, and then when it's done, you ended up with a total mass of 37.96. So if you take that and you subtract 37.55, how much water did you make? 0.41 grams of water. So the whole point is this, is that you burned some vitamin C, you produced carbon dioxide and water, and these are the masses of CO2, and this is the mass of water. So you can obviously see where we're going here. We can determine the number of moles of CO2 and the number of moles of water. All right, so the masses of, and what it's asking us to do is determine the molecular formula, okay, based off the combustion analysis. So it says here, the plan is that the masses of carbon dioxide and water produced will give us the masses of carbon and hydrogen present in the original sample. And then from this, we can determine the mass of oxygen. All right, and how are we going to determine the mass of carbon in 1.50 grams of CO2? By the mass percentage, right? How are we going to determine the mass of hydrogen in here? The mass percentage, right? And what's going to be left over will be all oxygen, okay? Then we've got the mass of the carbon and the hydrogen and the oxygen. We can figure out the molar ratio. Boom, we will have a formula. All right, so let me work with you guys here. And let's take a look. And some of these I've already gone ahead and done the math that we've already looked at. And so I'm just determining from mass percentage, right? I'm just using mass percentage. So the mass of carbon in my carbon dioxide, I know that there's 12.01 grams and 44.01 grams of carbon dioxide. So I end up with a total mass of carbon in that 1.50 grams of CO2, 0.49 grams of it are carbon, right? in my water, using the same approach, okay, in my 0.41 grams of water, this much of it is hydrogen. Okay, so if we want to know how much oxygen we have, we take the mass of the vitamin C, okay, and they gave us that way back at the beginning of the problem, right? We started it with 1 gram of vitamin C, okay, and we're going to subtract the mass of carbon and the mass of hydrogen, and we're left over with the mass of oxygen. So there's one little thing here. I'm lecturing to like 100 people right now, so I would be remiss if I didn't go back and mention something, and I might rewrite this problem for next semester, or the next time I teach this class, which I don't know when that will be because I'm teaching Gen Chem 2 in the spring. But something that it left out here is that vitamin C is made out of carbon. It's only made from carbon, hydrogen, and oxygen. I guess you would assume that based off of what's given to you here, but I don't know. Students don't always assume, you know, everything that they have to. And so I would put that in, that those are the only 3 elements in vitamin C. Okay, so with that in mind, it boils down to a problem that we've already looked at. You're like, what? We looked at this problem? Yes, we've done something exactly like this. We were given a problem a few minutes ago where we had the mass of every element and it said figure out the formula, right? So we did it. All right, so with that in mind, take a look. What are we going to do? We're going to figure out the number of moles of each one of those elements by dividing by their molar masses. And when we do that, you can see that you get this many moles of carbon, this many moles of oxygen, and this many moles of hydrogen. What are you going to do? You're going to divide all of them by 0.046 moles. Divide by 0.046 moles. Divide by, and Mike, did I not choose the right one? You know what? Is anybody else hungry? Or is it just me? I am like so hungry right now. 0.0341 moles. 0.0341 moles. And if you're thinking, Mr. Deon, aren't you supposed to be the responsible adult and eat a proper breakfast before lecturing? Okay, well, my defense is this is my first time in my whole career at UCCS that they made me teach 2 classes right in a row. So I literally have no break. And so it's kind of hard to adjust your diet for 2 straight lectures. Normally I would have a period off, you know, where I could go have a snack. Anyway, that's me rambling on. When you divide all those, you get ratios of 1 to 1.3 to 1. So what are you going to do? You're going to take all of those, and you're going to multiply by 3. Then you end up with 3, 3.9, and 3. And that's close enough for C3H4O3. I know there's somebody out there who's listening to me who's thinking, well, how do I know that I round the 3.9 up to a 4? Well, if it's that close, you can assume that you don't have to multiply 3.9 by, you know, some other number or anything like that. And on your exam, I will always give you a ratio that should be abundantly clear to you. Okay, so now we have the empirical formula, right? But we don't have the actual molecular formula. And so we divide the molar mass by the mass of the empirical formula. We get 2. And so we take this empirical formula, we multiply it by 2. And that is the formula for vitamin C. Vitamin C. Okay. And you can even go Google that to be sure that there's not a mistake there. That is the formula for vitamin C. Good stuff. All right. Does anybody have any questions? Because we're going to switch gears a little bit here. Does anybody here enjoy math? Am I the only person that likes the math part of chemistry? Just me? Okay. All right. Well, I enjoy the math part of chemistry quite a bit. All right. We got a few people. Good. All right.
For combustion reactions, are they just going to be for like the organic compounds like carbon, hydrogen, oxygen? Because on the Learn Smart, I clicked that as the option and it said it was wrong. So I don't know.
You'd have to take a screenshot of that for me and show me exactly what they're talking about. So if you have a complete combustion, right? If you burn a hydrocarbon like octane, let's say in your gasoline tank, I mean, according to what we just talked about in that problem, it said the only thing that you get is carbon dioxide and water, right? But if you go all the way back to that slide that I said I would skip, it kind of skates over here, right? You got water, carbon dioxide, and other substances. Okay, well, there's definitely, if you have incomplete combustion, which is what happens when you burn octane in a gas tank, that's why you end up with things like carbon monoxide, right? Because of incomplete combustion. So is it always going to be just cut and dried that you only get H2O and CO2? No, okay? Anyhow, again, send me a screenshot if you have a question about that, and I'll take a look at it. Just before we move on to chemical equations, I'll just kind of give you a heads up about the math thing. So when I was where you are, I was in my first semester at the university. I lived in residence, and we used to go eat at the cafeteria. And there were some guys there sitting at the table, and they were in second year students, and they were taking organic chemistry, and they were talking about organic chemistry, and they said, organic chemistry is impossible. It's so difficult. You're not going to believe it. It's going to blow you away. You'll never figure it out. And of course, I became an organic chemist. But anyhow, and I was like, what makes it so difficult? Why is organic chemistry so difficult? And again, I hadn't studied it at this point. I was, 18 or 19. And what they said was, well, you know how in general chemistry you had a calculator all the time? I said, yeah, I remember that. And they said molar masses, formula masses, mass percentages. Yeah, I remember that. They said, well, in organic chemistry, there's no calculators. Okay, we never calculate anything. And I was like, well, sounds kind of interesting. So if you're a person that doesn't relish the mathematical aspect of chemistry, maybe organic chemistry is for you. But the bad news is that you'd have to take 2 semesters of general chemistry in order to enroll into organic chemistry. Well, that was a little break, and we got 9 minutes left. So let's talk about chemical equations. A student sent me a question about chemical equations, and so I'm going to try to rectify some of those questions that my students might be having about chemical equations. It says here, a chemical equation uses formulas to express the identities and the quantities of substances involved in a physical or a chemical change. And so here's the reaction or the chemical equation that of interest. It's on the slide, but I'll just kind of highlight it for you. Is that it's saying you have H2 gas, so hydrogen gas plus fluorine gas gives you 2 molecules of hydrogen fluoride gas. Okay, so I know that that's written right here, but I just wanted to make it bigger. So it's saying you're taking 1 mole of hydrogen, right? There's no, we call this number the coefficient, the number that's at the beginning here. When there's no coefficient, you assume that it's 1 mole of hydrogen plus 1 mole of fluorine gives you 2 moles of hydrogen fluoride. Okay, good enough. Now we know from the periodic table that if we have 1 mole of H2, we have 2 hydrogen atoms, that would have a mass of 2 grams. So that means we're taking 2.016 grams of hydrogen, we're combining it with 1 mole of F2, which weighs 38 grams, and we end up with 40.2 grams. You can check the law of conservation of mass. If you take 38 and you add 2.016, you end up with 40.02. If we divide those masses by Avogadro's number, okay, that's what's being done here, we see that we have 1 molecule of hydrogen reacting with 1 molecule of F2, and we end up producing 2 molecules of HF, okay? And this is a balanced chemical equation based off the law of conservation of mass, that we cannot create or destroy matter. Look, we started with 2 hydrogen atoms here. We started with 2 fluorine atoms. Well, that's how many we have over here. Okay. An equation must be balanced. That means we have the same number and type of each atom on both sides. So let's take a look at this example here and see if we can balance this equation. It says we have magnesium plus oxygen gives us magnesium oxide. Okay, that's fair enough. Is this equation balanced? The answer is no, it is not balanced, because you see that we have 1 atom of magnesium and we have 1 atom of magnesium over here. Okay, that's not too bad. That's balanced. But what about the oxygen? Is that balanced? Well, let's take a peek. We have 2 atoms of oxygen here, but only 1 here. So how are we going to balance this out? Let me show you. Okay, there's a couple of ways you could do this. One of the easiest ways would be to say, well, instead of 2 atoms of oxygen, what if I multiplied this by a half, right? A half times 2 gives me 1, right? 0.5 times 2 gives you 1. So what I have now is a completely balanced equation. Now, something that I've learned since immigrating to America is that down here, they don't like to leave fractions in balanced equations. It is balanced the way I have it written, but down here in the States, my fellow instructors always say, you have to have it balanced with whole numbers. And so how would I balance that in whole numbers? I would take everything, and if I want to get rid of this 1/2 fraction, I'd multiply the whole thing by 2. Then I'd end up with 2 mg plus O2, because a half times 2 gives you 1, produces 2 moles of MgO. Now let's double check. I have 2 atoms of magnesium, 2 atoms of magnesium. I have 2 atoms of oxygen and 2 atoms of oxygen. There we go. So now my equation is fully balanced. All right, so that's one strategy you can take to balance the equation. Another strategy, and I'm sure people have tried this, I'll erase this spinach that I have up here, okay? Another way you could do it is to say, okay, well, if I have 2 oxygens right here, why don't I put a 2 right away in front of my magnesium oxide? So now my oxygens are balanced, right? I have 2 oxygens and 2 oxygens. But now my magnesium is out of whack. But that's easily fixed because I have 2 magnesiums here, so all I have to do is put the number 2 there, and I'm done. All right, so that's how you balance equations. And equations can be much more complicated than this, but this is sort of an initiation in how to balance a chemical equation. All right, so here's some steps that might be handy for you in balancing chemical equations. Translating the statement, it says we first translate the chemical statement into a skeleton equation. Then we adjust the coefficients. Remember, the coefficients are the numbers at the beginning of a formula. In most cases, the smallest whole number coefficients are preferred, so no fractions. I mean, it depends on where you look, right? I like fractions, but I've learned that down here, textbooks don't like fractions in their equations. What else? You can always check after, right? You can check it to make sure that it's balanced. And then also always specify states of matter in a balanced equation. And if you're like, what the hell is a state of matter? Let me tell you. The state of matter is solid, liquid, or gas. So if your compound is a solid, you put an S in brackets after. If it's a liquid, you put an L in brackets. If it's a gas, you put G. There's one more state of matter that we're going to see in balanced equations throughout this class, and that's a solution, an aqueous solution. And for that, we put AQ. All right, there we go. So a 3-level view of a reaction. Here's a reaction between magnesium and oxygen. I'm sure there's somebody who's listening to my voice right now who's tried this reaction. So magnesium undergoes combustion in oxygen to make magnesium oxide, and it produces a really bright flame. It's so bright that you shouldn't even look directly at it. But if you look at the microscopic level here, what the hell is going on? We have our magnesium metal, where we have all of our magnesium atoms closely associated with each other. We have our oxygen atoms, which are oxygen is a diatomic element. Remember Brinkelhoff or Have No Fear of Ice Cold Beer, and that's why oxygen exists as O2 gas when it's by itself. It's one of the allotropes of oxygen. So those combine and they make an ionic compound, right? This is ionic. The oxygen loses electrons, gains electrons, and the magnesium loses electrons to form this ionic compound, which is magnesium oxide, which is a white solid. And so that's this crust that you see on the top of the flask is the magnesium oxide. All right, let's try doing some balancing. Want me to show you how to balance a combustion reaction? If you're tired, you're like 10:38, come on, aren't you done? No. And this is a really, I can give you Mr. Deon's patented method for balancing combustion reactions that you'll nail it every single time, okay? So it says here that within the cylinders of a car's engine, the hydrocarbon octane, CH18, one of the many components of gasoline, mixes with oxygen from the air and burns to form CO2 and water. Write a balanced equation. Well, first of all, octane is a liquid, so we'll put that there. Oxygen is a gas, carbon dioxide is a gas, and water, as if it's water vapor, so we'll put water like that. Anyhow, now we need to balance it. For any combustion reaction, listen to me very carefully. Always save oxygen for last. Okay? Balance the oxygen last. Worry about everything else first. Because whenever you have an element that's by itself, okay, it is like your trick. It's like your ace up your sleeve. Watch. You have 8 carbons here. I have 1 carbon here. So that means I must have to have at least an 8 in front of my CO2. Now my carbons are balanced. What about my hydrogens? I have 18 hydrogens here. I only have 2. What times 2 gives you 18? The answer is 9. 9 times 2 gives you 18. So now my carbons and my hydrogens are completely balanced. Now the last thing I have to do is balance the oxygen. Okay, it's the last thing I have to do. How many total oxygens do we have here? 8 times 2, which is 16, plus 9. So 16 plus 9 is equal to what? 25. So that means we have 25 moles of oxygen on this side, or 25 atoms, however you want to look at it. So what times 2 gives me 25? The answer is 12 and a half, right? But I'll just write it as 25 over 2. And if you're thinking, well, Mr. Deon, I thought you said no fractions. No problem. Let's take the whole thing and we'll multiply it by 2. And then our balanced equation will become 2C8H18 liquid plus 25O2 gas produces 16 CO2, which is a gas, and 18 H2O, which is also a gas. And there you have it, folks. There is your perfectly balanced equation, just like that. Okay? Somebody put, how can you know if a product is a solid, liquid, or a gas? Well, in this case, octane is in gasoline, and gasoline is a liquid. Oxygen is a gas in the air, so is carbon dioxide, and it tells us that the water is a vapor, and a vapor is a gas. And so here it's given to us. All right, well, I think that's enough for now. I've gone over a little bit. Feel free. I'm going to stick around for a couple seconds here. Where was I? Boop. Stop recording.